Okay. Yeah.
Okay. Thank you for the invitation. So it is my pleasure to present these seminars in these occasions. So the presentation's title is by single interaction interface for ethic human-robot collaborations in construction teleoperations. So Zhenghua give me a very nice introductions. So I'm currently the associate professors in CTU and also the council members for the Chinese Association of Young Scientists and Technologists. And luckily, I was also elected as the president-elect for ASCE Greater China sessions. So I believe that in the futures, we might have a lot to collaborate in terms of the outreach activities and etc. So myself is also a member of the Smart City, the Built Informatics and Smart City clusters at City University of Hong Kong. So this, please allow me to briefly introduce about these clusters. So these clusters is interdisciplinary clusters in our universities. So it includes faculty members from civil engineering, mechanical engineering, computer science, data science, College of Business, and also some members outside City University of Hong Kong. So that with this interdisciplinary nature of the cluster, we can conduct research across the life cycle of the project at different scales. So starting from the building levels to the community levels, or even to the city levels or the country levels. So as part of the clusters, my major research is in construction safety, construction digitalizations, and automations. Also, I work with building energies management. So in today's presentations, this is the outline of the presentations. So first, I will introduce the background and then talk about the classifications of human-robot collaborations, and then come to the human-robot collaborations interface. And then we will also talk about some of the challenge in HRC, and then we will demo some HRC applications based on our existing research, and then point out some of the future directions based on our understandings. So first, why construction robots? So here, these are some of the informations extracted from different reports. So for example, in 2017, the McKinsey Global Institute conducted a research to analyze the digitalization levels of different industries across in China and across the world. So here they summarize the digitalization levels in mainland China. So as you can see here, the construction industries is the industries with the lowest levels in digitalizations. And because of the lowest level of digitalizations, the construction industry's productivities is not increasing, but decreasing a little bit based on the studies of Construction Industries Institute in 2015. And also, you can see that in the construction industries, the safety performance is degrading in the past few years. And another challenge is that in different countries like China's, US, Korea's, Japan, and etc., the elderly problems is becoming more serious. And here shows one of the studies conducted in United States. It shows that the average age of workers in the construction industries is increasing. And based on one news that was released in Hong Kong a few years ago, they estimate that nearly 190,000 construction workers are going to retire in the next 10 years. And regarding the younger generations in Hong Kong, not many younger generations that are willing to work in the construction industries. So how do we solve the shortage of labor issues and also the productivity issues as well as safety issues? So the construction robots becomes one possibility. And in different companies and different research institutes, they actually pay a lot of efforts in developing different type of construction robots for architecture, engineering, and construction industries. So for example, like Japan, they developed the human joint robot to install the panels. And also this is the bricklaying robot. And also in France, they developed the FE bot that is used to move those materials over in the construction job sites. And the country gardens in mainland China, which is one of the largest real estate developers, they also invest a lot in construction robotics, so that they also develop different types, more than 16 different types of robots for the construction job sites, like the wall brick laying robot. This is one of the products. And besides the construction and real estate companies, many of the IT companies like Baidu in mainland China, they also start to step in these construction robots industries. Like Baidu, they collaborate with Hong Kong U to develop the unmanned automatic excavators and trial it on the construction job site. And for all those construction robots, some of those robots, they are only focused on a specific task, and their applications is relatively simple at this moment. So with the developments of construction robots, the construction industries is moving from the manual construction job site to the fully automatic construction job sites. So in the futures, we envision that the construction job site will be an fully autonomous construction job site. You will see less humans or less workers on the site. But this is still far away from our current practice. So in the middle, you will see that there will exist a long period of transitional phase. So in this period, you will have the humans and the robots working together on the construction job sites. So this is the humans-robot collaborations. And for human robots collaborations, there are different classifications method on it. So here give you one of the commonly seen HRC classifications method. So based on the studies of Beers in 2014, they divided the human-robot collaborations for the general industries into those different levels of robot autonomies. And for the construction industries, the HRCs is in the mainly in the first 3 levels, so that the other levels might not apply to the current stage of the construction industries. So to further classify the HRC in construction industries, we adopted another classifications method based on the studies published in 2003. So that in these studies, they classify the type of interaction roles that the humans might have when interacting with robots. So that the interaction roles of the humans can be classified into 5 different categories. So the first interaction role is supervisors. So that means that the humans will only act as supervisors. So they will give the supervisions to the robots when it is necessary. So they will not, the humans will not directly control the robots. And the second interaction roles is operators. So that the human operators, they need to have more interactions with the robots. They will step into the teleoperations of the robots or change the robots' behaviors. So that this is commonly seen in the construction industries. So that like the teleoperated excavators, robot teleoperations, and etc. And then the third roles of humans that can have in HRC is a teammate. So that in these roles, the humans will act as the teammate that is working in the same team with the robots. And then the next interaction roles is programmers. So that humans will do the pre-programming of the robots. So that robots will act according to the predefined paths and the commands. And the last levels is the bystanders. So that human bystanders does not control the robots, but requires some understanding of what the robots is doing in the same space. And this is a more high levels of the interactions roles. And as we analyze the HRC research in constructions in the past decades, and we found out that most of the current studies, they focus on the operators' roles for HRC in constructions. And here I give you the time demands chains of the HRC interaction roles in constructions. The studying the operators' roles of HRC in construction industries start a long time ago. So that before 2000s, researchers in construction domains, they already start to study the operators' roles of humans in HRC. And then as the time passed, some researchers, they focus on the teammates' roles, and also some lectures after 2013. You can see that some researchers, they start to study the supervisors, programmers, and bystanders' role of humans in HRCs. And in the human robots collaborations, there is one interface that do the communications between the humans and the robots. So that humans, they need to understand the robots' intentions, and the robots also need to understand the humans' intentions. So that here shows summarize different types of human-robot initiative communication method in HRCs. So these tables summarize some of the intuitive interface for on-site HRC. Like Professor Ryan's just introduced, the gestures type user interface. And the gesture command can be used to tell the robots what is the command that the humans want the robot to do. And also they can tell the directions or the spatial informations about the command. And the gesture command user interface is very user-friendly. However, they also have some limitations, especially when you're talking about the command that is represented by the gestures, because different users, they might have different patterns in the gestures representations, so that for the robots itself, they might have some disagreements of the gestures between the users. So this might cause some confusions for the robots itself. And the second intuitive interface for HRC is a voice command. So that the users or the humans will interact with the robots based on the user's voice. So This enables the complex instructions and the parameters decisions. However, the voice command might be less practical in the busy and the noisy work environment, because if you're using the voice command in those noisy work environment, the noisy backgrounds might obstruct the capturings of the command for the robots. And the next type is gates command, so that the humans can interact with the robots based on the user's gates. So the robots will analyze what the users is looking at, and then it can incorporate the user's visual focus of attentions. However, if you want to use the gates command for the HRC, they might require expensive eye tracking devices, and also they might be difficult in interpreting the user's eye tracking data. And another intuitive interface for the on-site HRC is biosignal command. So that for the biosignal command, the systems can capture the biosignals like the EEG or the EMG and etc. of the human operators. And then the robots can understand the user's psychological states. And however, there are also some limitations of the biosignal commands, like there might be some difficulties in stable data acquisitions and data processing. And then lastly is the vision-based proactive command, so that the robots can use the computer visions to capture the humans' behaviors. And then they can proactively plan and act according to the human's commands or the human's state in real time. However, there are also limitations for this method, is that the harsh on-site conditions might affect the algorithm's accuracy. So you can see that in these tables, different methods, they have their advantage and also have its limitations. So in the futures, if you can combine or fuse different methods together, this might also improve the performance of HRC. And here summarize the typical physical interactions interface that have been demonstrated in previous studies. So for example, like the first interface for HRC is the manual interface. So that humans, they will directly touch or control the devices or the robots. So for example, like the humans, they will touch the robots and then guide the robots. How do they actions in this physical environment? And second commonly used interface for human-robot collaborations is the teleoperations interface. So for example, like the humans, they use the controllers, joystick, or haptic master devices to control robots and receive the feedback of the robots in the physical environment. And the next commonly used interface that is proposed in some studies are the VR and the AR interface. And this has also been introduced by Ryan's previously, like the spatial augmented realities. So that the humans, they can put those commands using the augmented realities on the objects. And then the robots can understand those commands that is joined on those objects, and then take the actions. And then there are also some other interface, like the humans, they can use the laser pointers to point which panels they want the robots to focus or remove. And then the robots can understand those pointing positions. The humans, they can use the sensors that is mounted on the robots to do the interactions. And there's some different challenge for the on-site human robots collaborations. So here shows the 4 levels of collaborations identified by the Robot Safety Standard ISO 10218. So the level 1, the safety-related monitored stop method, provide a shared workspace for HRC. However, a human and robot cannot work in this workspace simultaneously. The robots undergo a safe standstill mode when detecting a human entering the shared workspace. And the level 2, a hand guidance method, programs the robots by moving the robots through physical contact. And hand guidance require robots equipped with both safety-rated monitoring stop speed functionalities, such as the robot switch between the normal working and the safe state. And level 3, speed and separations monitoring method, allow the human operators to share the same workspace by the safety-rated sensors of the robots. And level 3, that is power and force limiting method, that specify the limit of the motor powers and force to reduce the harmful consequence of human-robot contacts or collisions. And besides the safety issues, there are also management issues challenge for HRCs. So conventionally, like in the manual construction job site, you only have the managers and the workers on the construction side, so that the managers will provide supervisions to the workers. Then the workers will provide the feedbacks to the managers. So this is a very straightforward two-way communications between the managers and the workers. And in the HRC-based on-site constructions management, you introduce the construction robots that will work together with the workers on the construction site. So besides, there might also be programmers behind the construction's robots if the construction robots is programmed by the programmers. So that the management framework will change a little bit. So you have the managers, they supervise the workers, and then the workers, they will collaborate with the construction's robots together. And then the feedbacks might be provided to the programmers or provided to the workers, and then they need to report it to the managers. So in a more efficient way of the communications between different stakeholders on the construction job site is to use a digital framework for HRC in the on-site constructions. So that in this proposed digital framework, we have the robots, physical robots, and also have the robots simulations systems. So that with the digital twin of the construction's robot and the construction job site, you can feed the data from the physical world to the digital world, and then do the simulations in the digital world, and then send the feedback to the physical world again. And then for the managers and the workers, they can use the HRC's interface to interact with the robots systems on the construction job site. And there also, next, we will introduce some of the HRC applications that we are working right now for HRC. So the first project we are working on is the human robots teleoperations for the future constructions. So in these projects, we are trying to develop the human robots teleoperations systems for the MIC's constructions in Hong Kong. So that we aim to integrate the 5G technologies, the edge computing, as well as robots technologies to develop such systems. So we are trying to develop systems that is similar but different than the Zoom Lions, the Livericons of Liverbirds, and the China's state construction engineering companies that they have already developed. So here shows the more details of these projects. So we are trying to develop the digital twin for the construction job site, and then using the digital twin, the operators, they can do the simulations, or they can sense the real scenarios in the construction job site, and then provide the feedbacks to the robot systems through the teleoperations user interface. And then in one of the key components in these systems is how do we develop the user interface of such systems, so that we do the user interface developments in the Unities. And we also develop one virtual construction job site in Unity and use this test bed to test our systems. And here shows the prelim result of our studies. And then in our studies, we propose two different prototypes. One is the full perspective desktop VR, and the other one is using two perspective desktop VRs. And then we want to test how do we balance the information's amount and the cognitive load for those operators. And nowadays, many of the teleoperating systems or the tower cranes training systems that only work for single tower cranes. So in our systems, we also develop the cloud-based systems for the multi-tower cranes simulations on the construction job site. So we have one servers here, and then there are different clients they can connect it to the same servers. And then for the HRC applications, we also need to manage the human factors. So for example, we need to manage the distractions of the operators, and also want to analyze what is the cognitive load of those operators. So here shows one of the possible solutions using EEG. And we also test these solutions for another applications. And it demonstrates that this can be extended to the HRC studies. And also the biosignals of the operators can provide useful information for the human-robots collaborations. So for example, as we mentioned, we can use the eye trackings to provide information about what the users is or the operators is looking at, and to estimate what is the intentions of the operators. And also we can, in the futures, we can use the EEG to analyze what is the intentions of the, and also the informations overload of the operators. And another studies we have conducted is to develop the flexible sensors that can be attached to human skins very easily. So that in these studies, we develop this hardware together with mechanical department and computer science departments. And then in the test, it demonstrates that these sensors is quite sensitive, and also the accuracy is really high. And then although in the previous studies, we just use these sensors to detect the twistings and stretchings of the human's skin, but these informations might also be applied to the HRC for the robots to understand the humans' behaviors and the humans' actions. And here shows the proposed biosignal interactions user interface for the HRC. So that here we can have the humans subject to do the experiment based on different biosignals sensors like EEGs, eye tracking sensors, heart rate monitorings, and etc. And those sensors informations can be fed into our systems for further analysis. And then these informations can feed to HRC for the HRC's user interface evaluations, as well as for the computers or the robots to understand the humans' intentions. And here we propose some of the future's directions. So one of the future directions in HRC might be how to manage the teleoperators information's overload. So that nowadays, for example, here you can see that those are the currently used teleoperations systems in the industries. So you can see that for many of those current systems, they have multiple screens. And with multiple screens, these provide you much information about the construction job sites and all the containers shipping industries. And but with much of those informations, these might also provide some redundancy informations to the users, and which might cause the information's overload. So how do you optimize this user interface design? These might be one future research directions. And then another future's research directions might be proactive interactions for HRC. So for example, like to use computer visions or the wearable sensors for the robots to understand the postures or the 3D informations of the operators or the construction workers on site, so that based on the current state of the operators, then the robots can use some advanced algorithms to predict the intentions of the construction workers, and then to plan what is the next actions of the robots. And besides the robots understanding the operators' intentions, another quite important issues is for the operators to understand the intentions of those autonomous robots. If those robots they are not pre-programmed by the programmers, then the robots might act autonomously, so that how the robots can let the operators to understand what is his or her next movements. So that this is also a very challenging issues in the industries. And nowadays in the computer science industries, they already developed some algorithms that can plan the movement paths of the robots. So that based on the movement path plannings of the robots, it can let the operators to better understand what is the next movement or next positions of the construction's robots. Okay, so this is all my presentations, and I would like to thank the Research Grant Council of Hong Kong and Shenzhen Science and Technology Innovations Committees for sponsoring our research in the field of construction's robotics. And also, I will acknowledge my PhD students Mr. Zhang Mings in conducting such research work, and also our collaborators in mechanical departments and computer science departments. Okay, thank you.